is Heisenberg Group Leader of the Quantum Gravity and Foundations of Physics Research Group at the Arnold Sommerfeld Center for Theoretical Physics and Munich Center for Mathematical Philosophy at the LMU in Munich. Daniele is a theoretical physicist who works on quantum gravity. I will spare you all the fields in which he works. Gravitational physics, fundamental cosmology. His wider research activities on the philosophy of science and foundations of physical theories, in particular, foundations of quantum mechanics and philosophy of space-time theories. Among his many publications, and most of them are article publications as I could find, Daniele has an edited volume also on, quite aptly so, approaches to quantum gravity towards a new understanding of space, time, and matter, which was published in 2009 with Cambridge University Press. Today, Daniele's talk will be on physical space and physical time. What are they? So here's the Socratic question again. What have we learned so far? And the next daunting and exciting steps. Daniele, take it away.
Yeah, thank you. Thanks for the introduction. I share my screen. Okay, so what I want to do is to give a brief and very sketchy overview of what I see as a journey from commonsensical, which in fact means Newtonian notions of space and time, in fact, through special and general relativity towards what I would say is a suggestion about physics without space and time in the fundamental description. So I would do that in steps, but really in a sketchy manner. I hope just to highlight the main conceptual points. There will be almost no formula, no technical detail. I'm happy to answer questions both about the conceptual aspects and the technical ones, if there are any. Okay, so I just recapitulate the space and time of common sense, which are to a large extent shaped by Newtonian physics. So we think of time as having a preferred direction. So, and we sort of agree on what time is. And we think of space as it's also something that we shared up to the relativity of inertial frames from Galilean physics. The point here is that this notion of space and time are physical because they influence the way we describe other physical systems. They determine, they influence the physical description of all the other entities, but they're not dynamical themselves. They're not somehow in themselves subject to the influence of other entities. And in the Newtonian picture, gravity is a force, indeed, is something that attracts body and makes material entities attract each other, and it works at a distance. So, as it was pointed out already by Dennis discussing Einstein thoughts, well, these are exactly the points that have been shattered by general relativity, but that move came in fact in steps. First came special relativity, and one way in which it can be characterized is that with special relativity, space and time become intertwined. I wouldn't really say identified because they maintain important distinctions, but they are intertwined with one another. Moreover, they become perspectival. We already have a perspectival notion of space in the sense that, as I said, different inertial frames in the Newtonian physics have different spatial measurements. Now the same becomes true for time. So to summarize the longer story, with a distinctive focus on how we operationally determine space and time intervals, and a focus, I would say, reliance on the way we communicate or such measurements. What came out was that indeed we have a set of preferred space-time directions that corresponding to inertial frames, But in order to characterize them, space and time have to disappear as independent concepts, because in going from one inertial frame, one inertial observer to another, there is a mixture of the respective time and space determinations, measurements. With that and with the constancy of the velocity of light came the idea that the causal structure, the set of events that can affect or be affected by any given event, as a non-trivial structure. So the notion of a light cone. Not everything can affect everything else or be affected by anything else. Notice that this is not true in Newtonian physics, exactly due to the possibility of action at distance exemplified by the gravitational force. In this context, the only absolute structure that one has is the space-time geometry, which is understood as homogeneous and isotropic, and this causal structure. Because of the constancy and then upper limit given by the velocity of light, no action at distance is possible. And this is an important move towards an understanding of physical interactions as necessarily local. You cannot affect other bodies at a distance. You have to interact locally with them. This is important because it brings quite naturally the idea that any type of interaction is mediated by a field. And a field is a distribution of something at every point in space and time. This is the local picture. This was brought to the full completion, in a sense, of this picture, including the gravitational interaction by general relativity. What happened in a word, in a single sentence, is that space and time become physical themselves, dynamical and relational, and in a sense that I will try to clarify, also approximate notions. So let me say more about general relativity. There are two main points. One is on this slide, and the second is on the next. So the first point is that the current understanding, as Dennis pointed out in the first talk, is that you can identify, at least mathematically, then it's up to you to judge which picture is more useful. You can identify, at least in your mathematical model, the gravitational interaction with the determination of space-time geometry. And determination of space-time geometry, you simply mean the collection of statements about all possible spatial distances between events, time intervals, the curvature, volume of regions of space, areas of surfaces in space, and so on. Second, that gravity has to be described by a field. All that is implemented by introducing the metric field alongside the other interactions, for example, the electromagnetic interaction, also described by a field. And the theory gives you a dynamics for such a field, that is a dynamics for spatial distances, time intervals, volumes, and so on. Now, the dynamics in this case really means that this new field is a physical system. So all these space and time statements, so space and time themselves become a physical system. A physical system means that it affects and it is affected by all the other physical systems. It does possess non-trivial interactions with all the other entities like matter fields, particles, or electromagnetic field, and so on. So this relation is encoded in the Ansatz equations, which, as Dennis pointed out, basically tell you how the mass energy of material bodies deforms space-time. So it modifies the geometry of space-time, and vice versa, how the deformation of space-time affects the motion of all the other material entities. The immediate consequence of that is that for generic solutions, so for generic configurations of the gravitational field of space-time geometry, you cannot really identify preferred spatial or temporal direction. So there's nothing like an absolutely given temporal direction or an absolutely given spatial direction that everybody would agree on. Second, you can in fact show that specifying the geometry of space and time is basically equivalent up to one variable to specifying the causal structure of the world. So specifying all the possible cause-effect relations between events in the world. So if the geometry becomes dynamical, if the geometry of space-time become a physical field, a physical entity in itself, governed by its own equations, the same should be said about the causal structure. So the causal structure is also itself a physical system and is not a given background absolute structure. So this is the first lesson. When we say that space-time is a physical system in itself, we mean that it has its own independent degrees of freedom, in addition to the degrees of freedom that determine the properties of matter or particles or all the other interaction fields. And this is beautifully exemplified by gravitational waves. There is something independent about space that you have to determine by an appropriate set of equations after you have determined the distribution of matter, of all the matter content of the universe. There's something more somehow in the universe on top of all the possible matter components, and that's the gravitational field or space-time itself seen as a physical system. A second point is it comes from a more technical aspect of general relativity as a mathematical model. So I will only state the mathematical fact, and then I'll try to illustrate some consequences. The mathematical fact is a symmetry of the theory. It's a gauge symmetry, more precisely, of the theory, which is the invariance under some particular mathematical transformations of your mathematical model, in which you have a metric and other matter fields on a given differentiable manifold. So you can apply some transformations called diffeomorphisms, and they leave the theory invariant. So somehow physics is not affected by these type of transformations. Now, the technical aspect is not so relevant. The consequences are quite radical, because what these transformations do is to map the distribution of fields at a point in the manifold in your mathematical model to a distribution at some other point. The invariance under such matter basically implies that the points in the manifold, the directions in the manifold, the paths in the manifold basically lose physical significance, because you can map that description to the description of fields at a different point along different directions and so on. Now, this is important because it means that it's not the manifold in itself that is modeling space-time. Space-time has to be really understood in terms of other ingredients in the theory, even though the theory is formulated on a differentiable manifold. This is a non-trivial point, and believe me, it's a non-trivial point for physicists as well, including many people who actually work on gravitational physics. But it's an important one at the conceptual level, because it means that when you when you work with your generativistic model, no function of manifold points can be observable. So your notions of events, time, or space has to be defined in terms of relations between the fields that you defined on the manifold, including the metric field. So time, space, events become relations among dynamical fields. And in fact, one way to construct a notion of point, time or space direction and observables in the theory is so-called relational strategy, in which you basically have to model clock and rods in order to give meaning to time and space. So you have to pick up some degrees of freedom, for example, matter fields in your model, and express the localization in time and space of the other fields as a function of them. So from this point of view, time is whatever a clock measures, and space is whatever a set of rods identifies. But because no realistic physical system behaves like an idealized clock and rod, our idealized notions of time and space are approximate notions in general relativity. So the one simple example is here. That's maybe almost the only formula among maybe one of the 3 or 4 mathematical symbols you will find in the slides. Suppose we have a situation in which you compute R, which is, say, the average curvature of your universe at a given coordinate value of time t. And then you also compute the average value of a scalar field phi at the same coordinate time t. Well, neither of the two quantities is an observable in the theory because they depend on a point on the manifold labeled by t, in fact, a slice on the manifold, your fictitious present. So in order to construct something that is actually physical, you have to invert the relation between the scalar field and the coordinate time and insert it in the other. So the only physical quantity is the average value of the curvature R at the moment in time defined by the value of the scalar field phi. So you use the scalar field as a clock that defines time, and in terms of that, you define the value of the other geometric quantity in time. Okay, the rest is, so the use of coordinates and so on, is just idealization of a more realistic construction that not always we can carry out. Now, if this sounds already a bit far away from the usual notion of time and space, and it is, well, with quantum mechanics, it gets worse. So quantum mechanics really brings a whole different world in a way, and in particular, a strong tension between any notion of locality and any notion of realism. So let me just, it doesn't say so many things about space, so I'll be very fast here, but it serves to motivate why we try to go beyond general relativity in our understanding of space. So there are many things we learn from quantum mechanics, which is the formalism by which we describe all the rest of physics except the gravitational field, except space-time as a dynamical physical entity. So we learned that the determination of physical properties of any material system can only be probabilistic. We learn that generic states, generic possible configurations of physical systems, of any physical system, are in fact combinations, superpositions of those in which any of the properties have as a precise value. So I give you an example. We are happy to say that we define a particle by how quick it moves and where it is. That fully specifies what we can say about a single point particle. Well, the position of the particle can take different values. It can be here on top of the laptop. It can be there on top of the other keyboard. Well, in quantum mechanics, a generic state for the particle is in a combination of the two. So, it's a combination of the states at which any given property, like the position, has a precise value. As a result, in a generic state for a system, properties do not have precise values. And that's really generic. It holds for any system in generic states. It's a very special case when they have a precise value, when observable properties have precise values. Worse than that, in quantum mechanics, there are pairs of properties that we normally attribute to systems that intrinsically cannot be simultaneously determined. There is no state for a system in which all properties can be determined with absolute precision. So there is some intrinsic uncertainty in the attribution of properties to physical systems. Now, there are more things, but the other important point is that if you consider systems which are composites of subsystems, in generic states, there is no way the subsystem can be understood as independent, even if they are spatially separated. They are very far away from each other. So there is a clash between a straightforward notion of a realism in which you simply attribute properties to individual systems and locality. Because that's basically what is the key paradox following from entanglement in quantum mechanics. There are quantum correlations between subsystems that somehow seem to transcend local exchanges. They seem to be there even when systems are far away and they don't interact, they seem to have nothing to do with each other. There may remain some correlation between the two. So this is a tension between realism and locality, but also with the notion of separability of subsystems and so on. There are a number of consequences. So why is this relevant for space? Well, the first point is that although quantum mechanics is extremely radical for our understanding of the physical world, it treats space and time just like, or almost like in Newtonian physics. They are fixed absolute structures. So, and this basic fact that is about the description of space and time in quantum mechanics, but also everything else I said before about the quantum description of physical systems is in fact in immediate contradiction with everything we do and learn in general relativity. The two frameworks are sort of in direct contradiction to one another. So if you ask me what are space, time, geometry, matter, if I'm rigorous about it as a theoretical physicist, I have to tell you, I have no clue. I have to tell you that because I have to choose. Either I give you the answer coming from general relativity, and it's a certain set of answers, or I have to give you the ones suggested by quantum mechanics, and it's totally different. We can sort of live with the contradiction between, simply because the physical situations in which both type of theories are obviously relevant are very extreme, far away from any everyday experience. Like the beginning of the universe, the Big Bang, the center of black holes. There are indirect consequences that can be seen, but we can survive. We survived so far without solving the contradiction, but it's clear that at least at the conceptual level, we need to solve it if you want to have answers about space, time, and matter. So can we merge the two types of insights? Now, that's the problem of quantum gravity, because it's the problem of bringing together the main lesson from general relativity. The space, time, and geometry is a physical system itself, with its own dynamics, its own physical properties, and so on. And that physical systems are quantum, have quantum properties, like all the others that we describe in quantum mechanics. So space-time itself should be understood as a quantum system, and we are trying to do that. Now, what I will do now is to start anticipating what we can expect about how the picture of space and time will have to change when we move to a quantum description of space and time. And this will be done now in two steps. So first step, suppose that quantum gravity is simply a quantum version of general relativity. We have a number of mathematical procedures, algorithms for quantizing classical theories. So let's assume that that's the only thing that should happen. We manage to overcome the technical difficulties and we have a quantum version of general relativity. So what happens is that space and time themselves will become quantum. That means indefinite in their properties, fluctuating, and I would just say definitely weird. More precisely, what does that mean? It means that we keep gravity as described by the metric. We just turn the classical fields of general relativity to quantized fields. Well, then it means that we should expect superposition, so the type of probabilistic attribution indefiniteness of geometric structures, geometric properties, and causal properties of the world. That will have the same type of indefiniteness or fuzziness or simply weirdness. there will be geometric observables that cannot be simultaneously determined in any possible situation. They are intrinsically uncertain. For example, now I make up an example. It could be that, yes, I can determine the area of this table, but if I do that, I'm preventing myself from ever knowing what is, I don't know, the future causal structure of everything that is going on in this table. Because the two sets of geometric spatial temporal properties do not commute from the mathematical point of view. In general, you expect that there's no sharp meaning by which I mean a definite attribution to space-time notions, events, position in space, time intervals, and so on. So, and at best, this type of precise determination will be true only in some approximation. And then geometric quantities can become discretized, like many quantum observables, like the energy of the harmonic oscillator. Anyway, so all these difficulties are, or will be, in addition to the already radical changes of our notions of space and time brought about by general relativity. If you think that that's terrible, well, it gets worse. It gets worse because what I assumed is that, well, the only thing I have to do is to take the classical fields of general relativity, like the metric, the gravitational field, and the other matter fields, and somehow turn them into quantum objects with the same degrees of freedom. Well, in most current approaches to quantum gravity, that's not what happens. What happens is that the theory is really a theory about new type of degrees of freedom, which are not spatial temporal in any obvious sense. They are not fields. They are not quantized fields either. They are something else. So somehow space and time disappear altogether from the fundamental description of reality. So space and time reveal themselves as emergent notions, something that has to be reconstructed in some approximation from something else. And the something else has no spatial temporal characterization. And again, I give you a number of examples. So the main point is that the new structures, whatever they are not fields. They are not smooth entities defined on some manifold whose relations define space and time. That's not what they are. They have to be not of this type. Now I'll give you some examples of what they could be in some models, and then I close. The main point is that any notion of geometry and matter and space and time should come out of some sort of collective behavior of large numbers of new type or degrees of freedom. In the similar sense in which, I don't know, any notion of fluid dynamics, viscosity, density, this type of things are collective emergent notions from the atomic degrees of freedom. They are not fundamental. So this is just an example. In some approaches to quantum gravity, this is what replaces the metric field or matter fields of classical general relativity. The world is made of purely combinatorial and algebraic structures called spin networks, which are graphs, abstract graphs, labeled by algebraic data, which are representations of groups. But there's no manifold fields and all of that, and differential geometry and so on. And the idea is that from this algebraic abstract entities, their collective behavior, they group together, they interact. At some point, you can approximate everything with something like a smooth space-time. So anyway, here what happens is that the universe, or if you want, space itself at the quantum level, the more fundamental level, is treated as a sort of very peculiar quantum many-body system, like the ones that make up all of matter, Okay, so I mentioned two directions and then I close. What makes the glue that binds together these abstract entities and sort of forces them or leads them to form extended, smooth spatial temporal structures. Surprise is in these approaches entanglement. The very property that in the usual quantum description of material systems on a given spacetime is in tension with our notion of local physics and space-time localized entities, seems to be at the more abstract level, I would say, first of all, mathematical, then if you're optimistic, is also physical, is the glue that binds together these more abstract entities to generate space-time in some approximation. The second point I want to mention is that second direction research is exactly to take seriously the idea that the universe and space and time emerge as a collective notion in the same sense in which a fluid and fluid variables emerge from atomic physics. And one tries to apply literally the same type of methods to show the emergence of general relativity and in particular cosmology out of the quantum dynamics of such abstract entities. So that the universe is really like a condensate, and general relativity is sort of the hydrodynamic description of such a weird quantum fluid. Enough weirdness. I thank you for your attention.